to another video on calculus, and we're going to be looking at linearization in a slightly different way. I have another video where I actually go through the process of using linearization to approximate a particular value. Here we're going to look at it from a slightly different perspective, in that we're going to actually see how big of a difference we're really talking about between a given value and a approximate value, or an actual value versus a approximate value. So what I have set up here is a function, y equals square root of x plus minus 3, and I've already got the derivative out done, and I've done this kind of implicitly, so I've separated the dy's and the dx's, and I've done that for a reason, and that'll make a little bit more sense in a second. Now over here, what I have is the graph of that function, and I also have the derivative line drawn at some arbitrary point. We're actually going to assume that point to be x equal to 4. That's either here or there for the graph. And the idea being is that when we use linearization to approximate another value, say maybe right there, that value that is just a little bit off from the actual curve is going to be a little different. But that's going to be under the value of dy. So that dy value versus delta y value, and we're going to define delta y as being the distance to the actual curve as opposed to dy, which is the distance to the tangent line. So dy is the distance to the curve, dy is the distance to the tangent line. So that's the change in y for the tangent line versus the change in y to the next point, quote unquote, wherever that arbitrary next point is on the curve versus the next point on the tangent line. So that's the difference between the dy that we're going to find over here versus the delta y that we're going to find over here. And what we're going to do is we're actually going to take dy, and we're going to say we're going to find dy. We're going to do this function here, so 1/2 times our value of 4 minus 3, which is, that's a pretty nice value because that's going to work out nicely, right, to the negative 1/2 power, and then times delta x. And here we're saying delta x is 0.8. Now some of you may be thinking, well, I thought dy dx always went together, right? And didn't you just say this was dx and then I said delta x? Well, what we're doing here is we're going to assume that delta x and dx are the same value here. And the reason we separated them was because we wanted to be able to talk, and notice I have them listed here in the same spot. We wanted to be able to talk in reference to the same change horizontally and see what does that do to the changes vertically up and down. So we've standardized, or we've unitized, or we've kind of created this locking section, if you will, where delta x and dx are the same value. So we're going over by the same amount so that we can compare the difference between the actual curve and the tangent line. So that's the purpose of locking in the value of dx, which is why we separated the dx from the dy. And then we're going to make the assumption that this is also equal to delta x, so that we're going to be using it over here as well. Okay? Now when we do this process, we end up with dy is going to be equal to 0.4. Now you can pause the video and run through that process yourself. You have 1/2 times 4 minus 3, which is 1. The square root of 1 is 1. And then since it's a negative exponent, it's going to be flipped. So 1 over 1 is still 1. So you still have 1/2 times 0.8. If you want to think of this in terms of, like fraction times a decimal, you can think of this as 8 over 10, right? So 8 over 10 is 8 over 20, which reduces to 0.4, or you could think of that as being 4 over 10, which reduces to 0.4. So either way, you get 0.4. So different ways to do those calculations. Now let's go over here. So with delta y, we're going to be doing f of x plus delta x. Well, x is 4 plus delta x was 0.8, so we're actually doing 4.8 here. And then minus f of x, which is just 4, right? Well, that's a fun calculation to do, right? It's not terribly difficult. But what we do is we take 4.8 and we plug it into the function, right? So we're talking about doing the square root of 4.8 minus 3 minus the square root of 4 minus 3. So we end up with the square root of 1.8 minus the square root of 1. And when we do that, we get a value that is approximately 0.3416. And it keeps going, right? Which is decently close to our dy. So here we found delta y is close to dy, which means that there's just a tiny little bit of space. There is some error between those two. So if we wanted to know what's the error between our approximation and our actual, the error here would be 0.06, right? With some other decimals, if you will. But 0.06 is the error between those. So our error would be, in this case, dy minus delta y, which in this case would be approximately 0.06. Okay? So, I hope this was helpful. I hope this helped your understanding of tangent lines and what they tell us about the curve and other things that we can use them for. They're not just for finding maximums and minimums, but they also can tell us about approximations and how close some approximations are to actual values, which is this idea of error. And a lot of times we use this idea of error, like how close are we actually getting here? And in some cases we think, well, finding this actual value with some functions is extremely difficult. But if we know the error is going to be small, we can go ahead and use the approximation to have a good idea of what we're dealing with. All right, take care. I hope you enjoy this video. Reach out with comments and questions.